where was I? Okay, so I was on this slide, I think, here. Here's what they assumed happened. Let me go back a slide just because I got stopped here. They assumed if light was a particle, this is what you would expect to see. Two lines as things basically phase through these holes. But here's what actually happened. Since light has the ability to diffract, some light made it through this hole right here. Huh. Apparently I can't draw on this slide. It wasn't an issue. As soon as I draw there, look at that. That's weird. Nope. I know. That's why I need to move the slide. That's why the problem is. Okay, how do I fix this? Set as background? Oh, that screwed things up. No, it's way too small. Okay, well maybe I can draw on this now at least. There you go. Okay, so light's supposed to go through this little slit right here, right? And similar to light going through that opening, it now starts to spread out in like a wave pattern. What ended up happening is interference occurred. And so as these two waves interacted with each other, we got this pattern over here, which has now been drawn on. Okay? And it basically was a whole bunch of consecutive lines. And I'd like to show you guys this with basically a laser pointer and this little diffraction grating right here. Okay, so watch. I'm going to shoot the laser pointer at the wall right here. Right. Now watch what happens when I shoot it through this diffraction grating. Can you guys see how now there's a whole bunch of different spots all over the place? There's one over by the spray bottle. There's one right in the middle of the screen. As I shoot them through different ones here, I can actually create a whole bunch of different patterns here. This is known as an interference pattern, where light as a wave is starting to interfere with itself. And it's starting to cause these things right here to interfere and make this pattern. And over the next few slides, I want to try to show you why it did that. So okay, let me show you this one more time. Here's just the single light source. As soon as I shot it through a slit, it all of a sudden caused, this is known as an interference pattern here, which is kind of cool. So let me try to explain this on my future slides here. Here's basically the concept. As the light started to go through these two slits, it started to diffract and go out in wave fronts. Okay? Every time that a wave front meets another wave front, you have what's known as positive interference. And so let me find you a point of positive interference here. Right here, and right here, and right here, and here, and here, and here, and here. See how these two lines are overlapping right here? That's where two wave crests are meeting each other and creating a positive interference pattern. One wave is currently, at its peak, and a second wave is also currently at its peak, and they've met each other, and it's making it even stronger. We call that positive interference. And I've got some more slides to illustrate this concept right here. Yeah. That's actually what I got right on the slide here. Perfect. Okay. So let's say you have two waves that are considered in phase. Both of these waves right now are exactly lined up. So this wave right here and this wave right here are both at their peak. What ends up happening is they become even stronger. It becomes amplified. But like with sound, you can actually have this wave right here and this wave right here being completely out of phase. And what ends up happening is this tall part and this like below part, they cancel each other. We call that destructive interference. I mean, that's what signal jammers, UV, shh, thank you. That's what signal jammers do, is they try to create a destructive interference to try to prevent like a radio wave from being sent out. Okay. I've got more pictures here. Let me try to explain with the pictures here. Oh, not that one here. Here's kind of the basic concept here, is that as these wave fronts are going out, all of these red dots right here, where these two different things have aligned, they're all considered positive interference, or a wave crest and a second wave crest, they're adding to each other. And so what ends up happening is over here, on the wall right here, you get a dot. And same thing right here. These ones right here, you get a dot. And right here, you get a dot. And right here, you get a dot. And right here, you get a dot as well. However, there's also times where you get negative interference, where things are like canceling each other out. And that might be these blue ones right here. Now, in those cases right here, they would also add to each other as well. And so now what you're going to have is the low section combining with another low section right here. And so maybe you'll get some more dots due to this one and due to this one and due to this one, and due to this one. But what about in between? Well, like somewhere in the middle, like here, what you're having happen is one is up, but the other one is down, and they effectively they cancel each other. They destruct, they destroy. Okay. I don't know what you guys did, like perhaps with you guys ever do this with like springs or with what's the thing called? You move back and forth. No, not a pendulum. Shoot, what's it called again? Like the slinkies. You guys ever use slinkies in Physics 20? Do experiments with those where you like can send a pulse through a slinky? I'll see if I can find one and try to show you the idea. But you can basically cause positive interference and the wave gets bigger and bigger and bigger. Do you guys ever learn the word resonance from Physics 20? Is that a term you're familiar with? That's kind of what we're discussing here, is when waves build on top of each other, they amplify. You're getting resonance, right? When waves go out of sync, then they don't. Okay, so that's kind of what I'm trying to describe in these pictures here. Let me go back to this slide right here. If you were to, like, say, drop two rocks in the water, let's say this guy threw a rock and this guy threw a rock, you could actually see the ripples going up and down and up and down, and in the middle, you'd actually have where they interfere with each other. Sometimes it's positive, sometimes it's negative. Okay. So one more time. If they are in phase with each other, this is like resonance. And it's going to build and make it even stronger because they are in phase. But sometimes they're out of phase. So let me go back now to my demonstration, and let's talk about what we're seeing here with all these lines on the wall. Okay. There is a line basically directly in front of me. See how that line right about there? As I put the pattern there, there's still one right there in front of me. Okay. But there's also now ones that are like, I don't know, about a meter stick away from each other. The reason why is that the one that's right there, right, so it was right here, now it's going to be over here. That one right there, that's positive interference. And way over here, this guy is also more positive interference. What's happening in between them, though? Like destructive interference, where it's like it's canceling each other out. Okay. This was more evidence, then, that light has the ability to behave as a wave as opposed to just as a particle. And so it's known as Young's double slit experiment. Although I'm doing my best to try to describe this, I totally understand if it doesn't fully make sense yet, because this is very like conceptual. So I've got 3 different YouTube videos I want to show you that hopefully will help solidify what we're talking about here. So be patient, I guess. I'm just going to play them one at a time. Fariba, can you hit the lights, please? And hopefully by having somebody other than me describe it, hopefully this will help sink in. So here's a couple of YouTube videos I'm going to show you on the same concepts. We're going to start with this one right here. This one's a little bland. It's pretty boring.
Interference in light waves from 2 sources was first demonstrated by Thomas Young in 1801. A schematic diagram of the experimental setup is shown here. Light was made to pass through a slit, SO. The waves emerging from this slit was made to pass through 2 parallel slits, S1 and S2.
So hopefully we'll see the interference pattern here now. Can you guys see how it's like, it's bright here? And it's dark here. And it's light here and dark, right?
Thomas Young observed that the light from S1 and S2 produced on the viewing screen a visible pattern of bright and dark parallel bands called fringes. What causes bright and...
I'm going to rewind it one more time because I think this is what I'm looking for here. Can you see how, as this is emanating out, can you see how this is a maximum, a minimum, a maximum, a minimum, right? As they're coming through, right? And what happens is right here, as this guy's maximum corresponds with this one's maximum, right where my cursor is right there, can you see how that's kind of a bright spot? Well, the same thing happens here, the same thing happens here. But right here, how there's a dark spot, that's because a maximum and a minimum hit each other and they destructively interfered. Well, keep that going through to a screen, and now you can see how you get the light, dark, light, dark, light, dark, light sort of pattern, which is the exact same as what we have right here, where there's light, nothing, light, nothing, light, nothing, as you get this pattern going on here. Okay. So I hope that kind of helps maybe like visualize it with a video. The next one I want to show you is an experiment that a guy did where he actually tried to create the double slit experiment. So I covered this one here. I want to try to find this video here now, and hopefully that'll also help. Where did I leave that video file, though? Oh, hang on. Close this guy. Here it is. Here it is.
What is light? What is light? What is light? That's a good question. What is light? Isn't that an element? Okay. For us, which are the light? It's light over not dark. What's the difference between blue light and red light? The color. It goes in your eyes and then you see stuff.
They range from white to red to orange to green, like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment of Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There, I found Thomas Young's hand notes from 1803.
I brought into the sunbeam and this little card, about 1/30th of an inch, and observed its shadow, either on the wall or on other cards held at different distances, besides the fringes of colors on each side of the shadow. The shadow itself was divided by similar parallel fringes along dimensions.
This is an experiment so simple that you could make it at home, and yet so fiddly that I've never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
You can take it out of the street.
Taking it out on the street.
I'd possibly interview you guys for about a minute. Nice kind of box.
And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see there's two openings, very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
The obvious thing you think you're going to see is two lines.
Two lines on the bottom of the box.
Yeah, I think it'll be one line for the two.
I can expect the whole box it up.
That would be a kaleidoscope of some sort.
A bunch of colors.
Probably, yes.
Right, guys? Different colors. Yeah, kind of look. You expected to see kind of one line. Is that what you did?
No.
I see dots.
How many?
And it's one circle.
Well, there's one in the middle strongest, two either side.
With two on the outside and multicolored. One in the middle is just white.
Over rainbow.
The rainbow color as well.
Quite a few colours and lots of little dots.
There are more dots appearing.
I think I can even see more dots. Spreading along. Yeah, that's amazing. And I can see kind of the dots now. Not tons, but I can see dots spreading.
So I'm going to pause. This is what, in theory, these guys are seeing inside the box. Right? And this is that same sort of pattern. Now, granted, mine's with red light. Right? And mine is very defined right here. But theirs, if I use the laser pointer, right in the middle, this is where the central maximums have met. This is the brightest. But then there's like a dark spot for a second. And then it's bright again. Then it's dark. Then it's bright. Then it's dark. Then it's bright. Now, granted, as you get further and further to the edges, it's not quite as powerful. Okay? And that hopefully makes sense. I've got some slides to explain why it's not quite as strong towards the edges. The reason why is distance. Okay? It's got to travel further along the angle than it does straight on, right? If I were to shine this at the board right here, the closest one is the one that was right here, because it only had to travel from me to there. But the one that ends up way over there on the corner, like here, watch again. There's going to be one that's right over by my jacket. Can you guys see how there's one right about there? Yeah, it's also reflecting back as well. But if you guys can see the ones over here, these ones are faint. And one of the reasons why is that there's more distance along this hypotenuse than there is straight on. And that means there's less wavelengths to interfere with each other because of the distance. So, Anyways, let's keep watching this video here.
Yeah, that's amazing. Yeah, that's incredible. And that's just nothing else apart from two slits. That's incredible. So all we're doing is we're putting the light through two very narrow slits side by side. How does this make any sense? There's some kind of principle involved in it. The average person's not familiar with it. It makes sense. I'm really like, I must find out why.
Welcome to the office, please, Thomas.